Alrighty, in this video here, we're going to be talking about 8.4 z-tests for a proportion. So our seventh objective here is to test proportions using the z-test. So hypothesis tests involving proportions can be considered as a binomial experiment when there are only two outcomes. Remember, that is either this is going to happen or it is not. And the probability of success does not change from trial to trial. Recall that the mean needs to be equal to n times p, so that's the sample times the probability of success, and the standard deviation is the square root of the mean times the probability of failure. For the binomial distribution, a normal distribution can be used to approximate the binomial distribution when n, or the sample size times the probability of success, is greater than or equal to 5, and when the sample size times the probability of failure is greater than or equal to 5. The standard normal distribution can be used to test hypotheses for proportions. So the test statistic for the z-test for proportions is as follows. So p hat would be the probability of the success that you had minus the probability of the actual success, divided by the square root of the actual success times the probability of, or the times the probability of failure divided by the sample size. And again, you can always find your probability of success by taking x divided by n. So how many successes did you have out of how big your sample is? This would be your sample proportion. Again, P is the population proportion, and the P hat is your sample proportion, and then N is the sample size. So the formula is derived from the z-score of the sample mean minus population mean divided by population standard deviation by simply substituting in NP for your population mean and the square root of NPQ as your population standard deviation, and dividing again by the numerator and denominator by N. So assumptions for testing a proportion. The sample is a random sample. Two, the conditions for a binomial experiment are satisfied, meaning there's two outcomes and every trial will not change. And then also the third thing to also always check is to make sure that NP and NQ are both greater than or equal to 5. All right, let's look at an example. So example 9, we're going to look at female physicians. The percentage of physicians who are women is 27.9%. In a survey of physicians employed by a large university health system, 45 of 120 randomly selected physicians were women. Is there sufficient evidence at the 0.05 level of significance to to conclude that the portion of women physicians at the university health system exceeds 27.9. So you can kind of see here our null hypothesis would be that our population is equal to 27.9. That part is our equal, or they put in decimal form too. And then the percentage of physicians who are women is 27.9. So that's what it is in words. The alternative hypothesis is to see, let's see, exceeds, there's the word. So that would mean that greater than 27.9%. And so the portion of women physicians at the university health system is larger than 27.9. That's what we're trying to test. So therefore, that is our research claim. We have a alpha of 0.05. So basically, we are good with 5% or less of potentially making a type 1 error. So the test statistics is, so as follows. We would need to do we would need to determine our sample mean. So I need to do some work here. So our sample mean, or our P in this case, would be what actually happened. So we saw our probability of success being 45 out of 120. I'm gonna pull up a calculator real quick. 45 divided by 120 is 0.375. So therefore, our z-score would be 0.375 minus the probability of the p-hat, or the probability, population probability, which would be 0.279, divided by the square root. Again, you would have to figure out, so we need to do our standard deviation, and that's figured out by doing the square root of NPQ, but we have to divide the numerator and denominator by the n. So basically what happens here, let me give you a better formula here. They just basically had you just plug it in. Maybe the one before that. Oh, okay, yeah. So, I don't understand that whole plug-in thing over there, but that z-score that it gave you at first, that's the one that basically what it does. I feel like the vocab on the other one is a little weird. Here you go. So there's your sample. That's how I just calculated here. My bet it should be this guy. And then this was the probability proportion of the population is what we're assuming. And then you do P times Q. So my probability of success was 0.279, but then I need to multiply that by 1 minus that. So here we go. So I'll do 1 minus 0.279, and that gives me 0.721. I would need to do all that and then divide it within the same square root of 120. So I'm going to type that in my calculator real quick. Say quick. So in this case, that would be control divide 0.375 minus 0.279 divided by the square root of 0.279 times 0.721 divided by 120. And when I do that, I actually get a z-score of 2.34473. All right. So the critical value of z for 0.05, again, using table E or just memorizing what it is, it's going to be the plus or minus 1.65. But since I'm looking at the greater than, I just need to see the right side. So I just need to know that it's 1.65 as my critical value using table E and using this guy right here. All right. So therefore, for the right-tailed, let me get to the conclusion. All right, so for the right-tailed test, the statistics is the right of the critical value, indicating to reject the null hypothesis. Our critical value is at 1.65. We actually calculated 2.34, so it is greater than it. So therefore, there is significant evidence to reject the null hypothesis. And then again, if you're using the p-value one, again, going to the 2.34 and then trying to calculate the, and we can do that again, just to give you another example of that. I have it still pulled up. All right, so again, we calculate 2.34 as our z-score. So that's 0, 1, 2, 3, 4. So that's 0.9904. So let me come back over here. So I get a p-value of, hold on. I get a p-value of point, so hold on, 2.34. So 0, 1, 2, 3, 4. So 0.9904. Okay, so that's what the p-value is, but this is a greater than, so it's the right side of it. So I would need to do 1 minus that, and that actually comes out to 1 minus 0.9904 comes out to 0.0096. So that would be what my p-value would be, 0.0096. There we go. So let me get rid of this part here. So my p-value, therefore, I got 0.0096, and we were trying to stay less than 0.05. So with this, I can say there is sufficient evidence to support the claim that the portion of women physicians at University Health System does in fact exceed 27.9%. So that's actually solving that in two different ways. We could have been satisfied with the z-score method, but we also did the p-value method as well. All right, let's do one more example to make sure you have plenty of examples to look at before you work on your homework. And then that will pretty much conclude chapter 8. All right, so in chapter 10, we're going to be looking at, does exercise reduce stress? So a survey by Men's Health magazine stated that 14% of men said they used exercise to reduce stress. We're going to use alpha equal to 0.02. A random sample of 100 men was selected, and 12 said that they exercised to relieve stress. So we want to use the p-value method to test the claim. Is it reasonable to generalize the results to all adult males or adult Americans? So again, our null hypothesis will be that the probability is equal to 14%. This would actually be the research claim because we want to say, does this actually stick with all of Americans? And then the way we can say that is the percentage of men who say they exercise to reduce stress is 14%. Now, on this one, the null hypothesis, we're basically just stating that it's not that. So in this case, that would be P would not be equal to 14% or 0.14. All right. So this, therefore, the alternate hypothesis here would be the percentage of men who say they exercise to reduce stress is not 14%. Our alpha was 0.02, but do remember that when we work on this, we need to divide it by 2, but we'll get to that point in a little bit. The test statistics then would be, again, I'm just going to write the equation so that we still have it. There you go. So in this case, the test statistics, so Z, my P hat was 12 out of 100, which is actually 0.12, easy math there. So 0.12 minus the 0.14 divided by the square root of 0.14 times 0.86 divided by 100. And you plug that into the calculator, that actually comes out to negative 0.58. Again, that's rounded to 2 decimal places. The critical value for Z, remember, I need to go to alpha divided by 2, so I need 0.01. When I look at that, that actually gives me the plus or minus 2.33. Now, remember, on this situation here, I need the plus or minus because it's a two-tailed test because it just needs to not be equal to it. So I can do less than that or greater than that. So the area on the Z table associated with negative 0.58, again, using the thing, and we can look at it again to give you another example. I just lose all this. I just hate that. Hold on. Let's go over here. So again, I'm looking for that negative 0.58. So I'm going to scroll up. So here's negative 0.5. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be 0.2810. So come back over here. So again, I'm over here right now. I see that it was negative 0.58, and I saw that I got 0.2810. Again, this is a two-tailed test, so we have to double the area. So the p-value here is going to be 2 times 0.2810. So in this situation, that's actually 0.562, which is greater than 0.02. All right. And then you can also have solved that on the z-score as well. That negative 0.58 fell between negative 2.33 and positive 2.33, and seeing that the p-value ends up actually being greater than the alpha. With both of those statements, we can definitely say we're not rejecting the null hypothesis. There's just not enough evidence. So again, there's just not sufficient evidence to reject the claim. Remember, the claim was the null hypothesis, that the portion of men who say they exercise to reduce stress is 14%. So again, it is not reasonable to generalize the results to all adult Americans, because the population from which the sample was selected is not all adult Americans. It was just males. And I caught that at the very beginning there. It's like, oh, this might work for males, but not all adults. All right, so there you go. So that will give you another situation on how you could use the z-test and the p-value methods for a proportion situation. If you end up needing more help or more examples, please reach out and let me know. But I'll see you in the next video.